Welcome to this next lecture on acoustics. So, in the last class we derived the Rayleigh integral, which gives the solution for pressure at a point r dash, okay, by integrating over a area of a radiator with a normal velocity Vn. This is a planar radiator, e to the power of minus j k, let us call it r by twice pi r ds. Okay. So we will use this now to find solution to the piston in a baffle. Let me just switch these. Okay. I will call this r, I will call this small r. Okay. So now we will use this okay. Now it is at theta, let us say. This is a receiver point. Okay. So from the origin it is at r. Okay. So its coordinate location is r, theta and phi. Okay. So in terms of Cartesian, coordinates, its x location is, we are measuring theta this way. So let us say it is here, it lands here, let us say. So it is r sin theta, and let us say we are measuring phi from here, we measure phi from x axis. So we measure phi. So r sin theta cos phi, that is the x location of this point. And what is the y coordinate of that point? That is r sin theta sin phi, right. This is the projection this way and projection this way. Then z is r cos theta, r cos theta. Okay. Now we have a surface point at this location r0 from the center. Okay. So what are the coordinates of that point? Radiator point, the x0 value is r0 cos phi 0. Okay. So this is phi 0. Then y0 is R0 sine phi 0 and Z0 is equal to 0. Okay. So I will make this as R. I will make this R, sorry. This will be made R. Capital R, capital R. Okay, and this is removed. Now this distance is what is R. You remember this was R vector minus R dash magnitude. Okay, so that is what we are calling as this scalar R. So the scalar R is this distance between the radiator and receiver, scalar distance. So let's call this receiver point as R theta phi, and we'll call the source point, radiator point, is R phi 0, R 0, phi 0 and theta 0. Theta 0 is pi by 2. So these are the coordinates of the transmitting point, radiating point and the receiving point. Now what is this distance R? Scalar distance R. That is equal to square root of x minus x0 whole squared plus y minus y0 whole squared plus z minus z0 whole squared. So if we compute that, we get square root of r sin theta cos phi minus r0 cos phi 0 whole squared plus r sin theta sin phi minus r0 sin phi 0 whole squared, and the root extends, plus r square cos square theta. Okay. So let me call this instead r theta phi, dot confusion. Let me call it r theta phi. Been wondering what to name it. I'll call it the receiver coordinate r theta phi. Okay. Now if we expand this now, we get square root of whole thing under square r square sin square theta cos square phi plus r0 square cos square phi 0 plus r square sin square theta sin square phi plus r0 square sin square phi 0, okay, minus twice r0 sin theta cos phi 0 minus twice r 0 sin theta sin phi sin phi 0 plus r square cos square theta. Okay, now whole thing under square root, mind you. Okay, let me maybe extend it like this. So this connect added to that gives me r square sin square theta. Okay, give me r square sin square theta combined with this gives me r square. Okay, then this and this give me r 0 square. Okay, then I have minus sin theta is also common here, minus twice r 0 sin theta okay, twice r 0 sin theta into cos of phi minus phi 0. Okay, so if I take this to the next page, take this to the next page. Okay, now here is the deal. We take r square outside, becomes r, and inside I have 1 plus r 0 by r whole squared minus twice r 0 by r sin theta cos of phi minus phi 0. Okay. Here now we make an assumption. Mind you, this is still r we are looking at. Okay. The distance from the radiator to a receiver, we are looking at that distance. Okay. So now we will say that r 0 by r is much less than 1. That means from the coordinate system this distance is very far. Okay, this is called the far field approximation. Far field approximation. Okay, or let me do this. Let me do this for now. Let me do this. Let me copy this here. Copy. Paste. Okay, so let me do this. So this is the Rayleigh integral. Somehow the r went missing, so we'll put it in there. This is the Rayleigh integral, and this is what r turned out to be. So before I make this approximation, let's discuss that part. Okay, so let me bring it in here. Okay. So now if I substitute r in here, what we get? We get P of r theta phi as the area of the radiator, j omega rho Vn e to the power of minus j k. R is now square root of r square plus r0 square minus twice r0 sin theta cos of phi minus phi 0 by twice pi square root of r square plus r0 square minus twice r0 sin theta cos of phi minus phi 0, and the area element is of course dr0 r0 d phi 0. Okay, that's the area element. Now with phi 0 r0 in the numerators, I mean here, and r0 phi 0 here, it's not amenable to a closed form solution. Not amenable to a closed form solution. Okay, so we are looking now for a closed form solution for a sound field from a piston in a wall. Okay, so what do we do? This when we do the far field approximation. Okay, in the sense we can't have r0 phi zeros in the denominator. We can't. Okay, so then what do we say? We have this r given by small r square root of 1 plus r0 square by r square r0 by r squared minus twice r0 by r sin theta cos of phi minus phi 0. Okay, here we say my r0 by r is very small, much smaller than 1, that is order epsilon. So this quantity is order epsilon square, this quantity is order epsilon. Okay, now if I do a binomial, I am going to drop this in comparison to this. If I do a binomial expansion of the remaining, r becomes equal to r into 1 minus twice r0 by r sin theta cos of phi minus phi 0. Okay, ठीक है. Now we will do a further approximation, which is, so this looks like now what, r minus twice r0 sin theta cos of phi minus phi 0. Okay. Now if we look at, if we substitute this to begin, no, that is a mistake I made, 2 goes away, this 2 goes away. Okay. Okay, the root of 1 plus epsilon is 1 plus epsilon by 2. Okay, so that 2 disappears. Okay, so now if I use this in the Rayleigh integral, what do I get again? I get pressure at r theta phi given by integral over the radiator area j omega rho normal velocity e to the power of minus j k into r, which is now r minus r0 sin theta cos of phi minus phi 0 by r minus r0 sin theta cos of phi minus phi 0 dr0 r0 d phi 0. Okay. Now in the denominator r and r0 are linearly compared. Okay. In the numerator, it is not linear, they come under e to the power of minus j k of some r minus r0. This means what? This is cos of k r minus r0 etc. plus j k, plus j sine of k r minus r0 etc. Okay. So whereas here r minus r0 is a linear comparison, here they come with a k and this entity is in radians now. Okay. Pi radians are 180 degrees, 1 radian is 180 by pi. Okay. So this is a nonlinear term. So because it is a nonlinear term, we cannot drop r0 etc. in comparison to r. We cannot easily drop this term in comparison to r because this is a nonlinear operator. Small changes in this can have big consequences, whereas in the linear case, if r0 is much smaller than 1, r0 sin theta cos phi 0 much smaller than 1. I suppose you see the subtlety over here. Okay. And therefore what do? In the denominator we will drop this term. So all an attempt to find a closed form solution. So in the denominator we drop this term. So what happens now? Let us see. If I take this, copy, paste. Okay. So if we drop that, I will drop it from here. This will become r and r0 dr0 d phi 0. Okay. So to write it specifically now, we write it as integral 0 to a, the radius of the piston, 0 to 2 pi all around the azimuthal angle, j omega rho, I forgot somehow the twice pi. Okay, the twice pi. Okay. So j omega rho un by twice pi r e to the power of minus j k r e to the power of j k r 0 sin theta cos of phi minus phi 0 r 0 dr 0 d phi 0. Okay. So, I will bring all the constants out. J omega rho u n by twice pi r e to the power of minus j k r, okay, and then integral 0 to a integral 0 to twice pi e to the power of j k r 0 sin theta cos of phi minus phi 0 r 0 dr 0 d phi 0. Okay. Now, this field here is if we look at it, this is my piston, sorry, this is my piston, this is my piston, and it's oscillating back and forth, okay, and it's, I mean, and phi goes here and comes back to 2 pi here, phi starts here, comes back to 2 pi here. So, this field now is independent of phi. Independent of phi. You can see that, right? If I have this sitting in a baffle oscillating uniformly back and forth, okay, if it cannot depend on phi, it is uniform, uniform in terms of phi, okay. So, what we will do is we will set phi equal to 0, okay. If we do that, my pressure at a certain r, at a certain theta, at a certain phi is given by j omega rho u n by twice pi r e to the power of minus j k r integral 0 to a integral 0 to twice pi e to the power of j k r 0 sin theta cos phi 0 r 0 dr 0 d phi 0. Okay. Okay. Now if we look at this term e to the power j k r 0 sin theta cos phi 0, okay. So, how does this look like now? This looks like cos of k r 0 sin theta cos phi 0 plus j sine of k r 0 sine theta cos phi 0. Okay. Now the cos of this always is positive, whereas the sine oscillates. As phi 0 moves from 0 to 2 pi. Okay. So what happens is this integral of 0 to 2 pi of this cosine term plus j sine term over d phi 0, okay, the sine term goes to 0 and cos term is even, so it doubles. Okay. So we will again write this as j omega rho u n by e to the power of minus j k r by twice pi r integral 0 to a and integral 0 to pi twice cos of k r 0 sine theta cos phi 0, then r 0 dr 0 d phi 0. We are almost at the end of time, so what I will do is I will close the lecture here and continue in the next class. Thank you.